All right, let's get started. We're going to look at a motion of a charged particle in an electric field. So this is 26.6. Okay, so we shall look at a motion of a charged particle in an electric field. Okay, so we saw that we could create a uniform electric field by using a capacitor. So let me remind you of that. So we learned that we could create a uniform electric field between the plates. So we shall use this to at least to see what happens. We shall use it to learn what happens when a charged particle enters an electric field. So we'll start off by making the capacitor. So we shall look at a capacitor. It consists of two parallel plates next to each other. Actually, let me make the plates farther apart so we can look at what happens. So we have two parallel plates next to each other, and we have charge positive here. So this is plus Q, and this is minus Q. So the electric field goes that way between them. So if we introduce a charged particle into this field, so for example, if we bring in a positively charged particle from here, traveling with a velocity v, the charged particle is going to enter this field and it's going to go like that because it will be attracted to the negative plate. So as soon as it enters the electric field, it's going to be attracted to the negative plate, so it will travel that way. So we will see what happens when this charged particle enters the electric field and how it is deflected in the electric field. So we'll say a charge that enters the electric field between the plates or between the capacitor plates will be deflected to towards one plate depending upon its charge. So let me draw it a different way. I'm going to draw it this way this time. Let's draw a charged plate like that. So let's say that this is plus Q, this is minus Q, and then let's introduce here a little hole from which we shall introduce charged particles. So we introduce a charged particle Q, and let's say it's moving with a certain velocity v naught x. Okay, so it's moving along the x-axis with a velocity v naught x. The electric field between the plates is downwards, so it goes from a positive to the negative plate. And so, assuming there is no electric field, this charged particle will travel straight through. So if we place a target here, this is a target. If we place a target outside the plate, the charged particle will travel straight through and hit the target. If instead once we put the electric field on, the charged particle will deflect that way and hit the target at some point. Okay, so we can find the deflection delta y for this charged particle when it enters the electric field of the capacitor. Okay, so let's start off by saying that initially charge Q is moving with velocity v naught x. So v naught x is a velocity along the x-axis, and the electric field is E in the y direction. So the electric field is along the y-axis in the y direction. Okay. So according to Coulomb's law, the charge Q experiences a force F subscript Q, which is Coulomb's force, and we can say the force is charge Q times the electric field E. And then we can say that by Newton's second law, the force on the charge is equal to its net force, and that's equal to the mass of the charge multiplied by acceleration of the charge. Okay, so we'll say m is mass of charge and a is acceleration of the charge. So we can then say that F subscript Q is equal to the net force, since it's the only force present, and that's equal to ma. Okay, so we'll put it together now. We'll say that the mass of the charge times its acceleration is equal to QE. Therefore, we can say the acceleration the charge experiences along the y-axis. Remember that the electric field is along the y-axis, so the acceleration is along the y-axis, and that should be equal to QE subscript y divided by m. So the charged particle experiences an acceleration in the y direction given by this quantity, QE subscript y over m. So we can say that, let's consider the motion along the x-axis and then along the y-axis. Okay, So at this point, let me bring the capacitor back down here, okay, and then we have our charge Q entering here. The electric field is this way. So ideally it will go straight and hit the target, but it enters and hits the target here. So this is delta Y. So let's say that the distance here from one end of the plate to the other is D. Let's call it D. We might call it X. Let's just call it X since it's along the X axis. So that's the distance between from one end of the plate to the other is X. And to be more accurate, let me extend this X this way, because really we are talking of when the charged particle enters and when it hits the target. So this is our X. So first consider the X motion, and we can say that in the X direction there is no acceleration. So we are assuming that there is no this is all in a vacuum, so there is no air resistance. Okay, so we can say that the distance X is equal to the speed v naught x times the time delta t. Delta t is time to travel a distance x. Okay, so it's just the time from one end of the plate to the target. And then consider the y motion. We have acceleration in the y direction, so the motion is uniformly accelerated. Motion is uniformly accelerated. So we can say that for the y motion, the delta y, so we can say y final is equal to y initial plus v initial in the y direction, delta t plus half a subscript y delta t squared. So this is from first semester kinematics. So we can say that y final minus y initial is the displacement delta y from the target, and it's equal to v initial y delta t plus half a y delta t squared. And we need to note that the initial y velocity is 0 since the charged particle is not moving in the y direction. So we can say that initially vy is equal to 0. Therefore, delta y is equal to half a subscript y delta t squared. Okay, so this gives us the deflection of the charge from the target delta y. And then we can place in there, we can say that from uniform motion along the x-axis, delta t is equal to x over v not x. Okay, so the time is just the distance from one end of the plate to the target divided by the speed that the charged particle enters the target with, enters the capacitor with. And then we also know that also ay is equal to qe subscript y divided by m. So we can put all this together and we shall say that delta y can be written as half a subscript y, which is q e subscript y over m, multiplied by delta t, which is x, divided by v naught x squared. Okay, so we've put this into the form which depends upon the distances and the speeds and mass. So we've taken out the time. So this is the deflection of the charged particle when it enters the field, when it enters a capacitor plate. So now let's look at the capacitor again and see what happens. So here is the target again. The charge enters through this little opening here and travels to the target if there was no electric field, but with the electric field it deflects that way. The electric field is this way. So once it hits the target, the velocity will be this way, v. So there's going to be a component of velocity v subscript y and a component of velocity vx. So the next question is, how fast is it traveling when it hits the target? So when the charge hits the target, we can find the velocity v. We know that x motion is uniform motion, so there is no acceleration. So we can say that v naught x is equal to v final in the x direction and then the y motion is accelerated. So we shall have that v final y is equal to v initial y plus acceleration in the y direction times delta t. And since v initial y is equal to 0, we shall say v final y is just equal to a subscript y delta t. From here then we can find v, so we can say that the velocity v is equal to the square root of v final x squared plus v final y squared, and direction of velocity is given by, let's say, an angle phi, which is given by the tangent inverse of v final y divided by v final x. So with this, we've calculated everything we need to know about the velocity, the motion of a charged particle in between the plates of a capacitor. Okay. Note that v final y is equal to a y delta t, which can be written as a subscript y, and the time is x over v not x. So we can write v final y that way, where x is the distance from one plate to the other, or is the length of the plates. Okay, so I think we've got everything we need. Any questions at this point? Okay, let's try an example on this. So v final y. So let's see. So let me rewrite this a little bit better. So v final y. So ay is equal to qe over m, and then we have x over v not x. So we can write v final y this way, and v final x, of course, is just equal to v not x because there is no acceleration in that direction. So let's try an example on this. Let me make the electric field a little bit stronger. Okay, so let me draw a diagram, I guess, for you. So I'm saying that this distance is 2 centimeters. The distance here is 2 millimeters. Electron enters this way and is deflected towards the positive plate. So if you like, we can go like that. So this is the target right here. So what you are looking for is this deflection delta y, and then the speed when it hits the speed at that location where the deflection happens. Okay, so this is the deflection we are looking for. So see if you can use the formulas that we've developed in order to find that deflection. M electron, I believe the electron was 9.1 times 10 to the minus 31 kilogram, and the charge on the electron is negative 1.6 times 10 to negative 19 coulombs. The negative sign just tells you that when it is in between the plates, it's going to be deflected to the positive plate. Okay, let's make the speed, let's make the force smaller, or the electric field smaller, so that the deflection will be less. Okay, so I'll make it a little bit smaller. So note the change. I've just made the electric field 5 newtons per coulomb instead of 50,000. The electric field was too large, as he pointed out to me. So to make it more realistic, let's make the field 5 newtons per coulomb. Okay, so that's the only difference. Yeah, I don't know what I was thinking, but I was making it up as I went along. So I knew there was something. Okay, so what is the formula that we're using for deflection, delta y? What is the formula for delta y? So I believe you have all the elements that you need for this. So I gave you Q, I gave you M, and then E is 5 newtons per coulomb. X is 2 centimeters, so 2 times 10 to negative 2 meters. V naught X, what was it? 3 times 10 to power 5 meters per second. So when you enter this into your formula for delta y, you should be able to find the deflection. So we shall have half times 1.6 times 10 to negative 19 times 5 times x squared, which is 2, x squared is 4 times 10 to negative 4, and then divide that by m, which is 9.1 times 10 to negative 31. V naught squared will be 9 times 10 to power 10. Okay, so you have, let me see, so we should have 1.6 times 20, so this is 32 divided by half, so I'll make that 16. So we're going to have 16 divided by 9.1 times 9, 81.9. And then we have 10 to negative 33 times 10 to the power of 31 is 10 to negative 2. Okay, so we should have something like this in meters. What is 16 divided by 81.9? 0.19. So that's how we should have it, something like that. So it will be 1.95 times 10 to negative 3 meters, which is more realistic because it's within the plate. And what are we looking for next? So we're looking for V final. What was the question? Let me see what the question was. What is the speed of the electron? So we're looking for the speed of the electron. So V final of the electron is the square root of V final y squared plus V final x squared. We know that V final x is just V naught x. So V final y is equal to AY delta. So what is V final y? Our formula was QEY over M multiplied by delta T, which is X over V naught X. So with this formula, we can find V final in the Y direction. We have Q, which is negative 1.6. Remember, the negative sign comes in here, so the deflection is in the negative direction for the delta Y, because the charge is an electron, so it's negative 1.6 for the charge here. So this deflection is in the Y direction, so it goes down according to the diagram I drew. See this diagram? So this is in the Y direction, it's in the negative direction. So the magnitude is correct, it's just that you just note that it's in the negative direction because it's an electron deflecting downwards. And then the same will apply for the velocity. The velocity will be in the Y direction. So if you put a negative sign and it comes out that way, so V final Y can be written this way. So I'll just put the terms together. 1.6 times 5 times 2 is 10. So we'll do that 10. And then we shall say 9.1 times 3 is 27.3. And then we shall have 10 to negative 19 times 10 to negative 2 times 10 to 31 times 10 to negative 5. So then V final Y can be written as negative 16 over 27.3. And then we have 10 to negative 21, negative 26, and 10 to the power 31. So it's going to be 10 to the power 5. So 21, that's 26. 31, that's 5. So 10 to the power 5. So what is 16 over 27.3? 16 over 27.3. So your speed there will be 5.86 times 10 to the power 4 meters per second. So that's our Y speed. So now we can calculate the total speed V as the square root of V final Y squared plus V final X squared. So we shall take the square root of 5.86 times 10 to the power 4 squared. Let's put a negative if you like. The negative goes away when you square it, and then this will be 3 times 10 to the power 5 squared for the X component. And that will give us the magnitude of the speed when it hits that target. So what does that give us? So the final speed is 3.1 times 10 to 5. So what is the direction of the speed? So V final Y is 5.86 times 10 to negative 10 to the power 4 divided by 3 times 10 to the power 5. So to make it simple, let's do it this way. Phi is tangent inverse of 0.586 divided by 3. So do tangent inverse of 0.586 divided by 3. The angle is what? 11.05. Okay, 11.1 degrees. So it's a very small angle, which is what we expect because the deflection is very tiny. So it's just a small angle. So let me illustrate it again for you. So this is your target. Electron enters here. Without an electric field, it hits the target. But with an electric field, it's going to deflect a little bit and hit somewhere here. So we found this to be 1.95 millimeters is the deflection. And then the speed here is what we found. That speed is a very small speed, so the angle is very tiny. See, so this is the angle we are talking about, this angle here. It's a very small angle, as you can see, only 11 degrees. It's a very small angle.